Hey, sixth graders! Today we're learning about interpreting graphs. We're going to be focusing on three things: how to look at a graph and kind of read it in relation to a situation, how to tell which graph matches a story, and finally, how we can use a quick sketch of a graph in order to solve a problem. All right, let's start with this example here. So when we look at this graph, we see we have time measured in minutes as our independent variable, and we're comparing that to speed in miles per hour. Anytime we have a flat part of the graph, like we do right here or right here, that's showing some kind of situation where the data is remaining constant. So in this case, it would mean time is moving because I'm going from 0 to 10 minutes. But right here, the curve of the graph is flat. So it means I'm maintaining that speed. Doesn't mean I've stopped. It means I'm maintaining that speed. And it looks here, if this goes from 0 to 10, this must be 5. It must be going about 4 miles per hour for that 10 minutes. Now when I see these sharp increases, that is showing a rapid acceleration. And then we're maintaining here a much faster speed of 25 miles per hour. This is a quick slowdown back to that 4 miles per hour and then remaining. So let's see what we have here. The horse walks at a constant speed for the first 10 minutes. Yep, that's what we noticed. Its speed increases over the next 7 minutes and then gallops at a constant rate for 20 minutes. That is a really fast rate for a horse to go for 20 minutes, I would think. Then it's slowing down over the next 3 minutes and walking at a constant pace for 10 more minutes. All right. In this example, we're going to practice relating a graph to a situation, finding the best match. So here's our situation. Jenny leaves home and drives to the beach. She stays at the beach all day before driving back home. Which graph best shows this situation? Well, I notice all of these graphs are comparing time as an independent variable to distance from home as my independent variable. So if she's leaving home, that's important information. That means she's starting from home. So the distance from home, if you're starting from home, is going to be 0. You're not any distance from home. This graph C is showing starting someplace other than home. So I know I can rule that one out. The rest of the story tells us that she stayed at the beach all day and then drives back home. Well, graph A shows leaving from home and turning around and coming back home. So leaving, going at a constant rate of speed away from home, and then turning around and coming back at that constant rate of speed. I don't really see this staying home all day. Graph B, well, here we have driving to the beach. The staying all day is a little weird here because she didn't stay very long, or the day was short, and then turning around and coming back. So my best choice of these three graphs is graph B. Last, we're going to talk about creating a graph in order to solve a problem. Let's figure out what our problem is. So Miley and Katrina traveled 10 miles from Miley's house to the movie theater. They watched a movie and then traveled 5 miles further to a restaurant to eat lunch. After eating, they returned to Miley's house. Sketch a graph to show the distance from Miley's house compared to time. Use your graph to find the total distance traveled. In this situation, I'm using my graph as a problem-solving tool. I know that what I'm trying to solve is the distance that she travels. So here I want the total distance traveled. Well, I'm going to sketch a quick graph. It's not going to be fancy because I'm using it for a purpose of solving. I do know, because I was told, that I want to create a graph showing distance compared to time. Well, I know, and you know from science class, that often time is going to be our independent variable. So this is going to show time. And then here I have distance from her house, from home. Now it's important to have those labels. They're going to help me understand what I'm seeing in my graph. So now my plan is to look at all of the information that I'm given. I see here that she goes 10 miles to the movie theater, watches a movie, and travels 5 miles further to a restaurant to eat lunch, and then comes back. So my graph is going to look something. I know I need that 10 miles. I need to go 5 miles further. So I'm just going to make some marks here indicating kind of every 5 miles. Doesn't seem like I need ones or anything here. They wouldn't be very helpful. So she goes from Miley's house to the movie theater, which is 10 miles away. So they wouldn't instantly get there, so I showed somewhat of a curve. They got there pretty fast. I think they got a ride. Then they watch a movie. Well, they're not going to travel while they're watching the movie, so time will pass as they watch the movie. And then they are going to travel 5 miles further to have lunch. Now notice I'm up now to about where my 15-mile mark would be, because this was 5 miles to go to the movie. This was 10 miles, or I'm sorry, 10 miles to get to the movie, 5 miles to get to the restaurant. Now they're going to eat, probably not as long as the movie, and then they're going to come back home. Well, these two flat parts of the graph, when they're watching a movie and eating lunch, don't have any distance traveled. But getting to the theater, getting to lunch, and then this trip home, which would be that whole distance of the 5 here plus the 10 here to get back home. So to solve my problem, I'm going to add those distances. Well, they went 10 miles to the theater, 5 more to get to lunch, and then they went the 15 miles home. So that's a total of 30 miles. The look back step of solving our problem is where I'm going to think about whether or not this is reasonable. Well, if they went 10 miles to the movie theater, then they'd at least need to come 10 miles back. 5 miles further to a restaurant, 5 miles back. Yeah, my 30 makes sense. So I can be pretty confident that they traveled 30 miles as their total distance.